You know, in the world we live in today, the next pandemic feels less like a question of if and more like a question of when. And while we hear a lot about vaccines, there's another race going on that's just as critical, the race for a cure. Which brings up a huge question. I mean, really, how do you fight an enemy you can't even see? One that makes millions of copies of itself before you even feel sick. It's a massive challenge, and it's pushing medical science to think in completely new ways, on a scale that's almost hard to imagine. Well, it turns out the best way isn't to fight it head-on. It's more like sabotage. Scientists figured out that instead of trying to destroy the virus itself, they could go after the microscopic machine it relies on to replicate. So, if you can break the copy machine, you stop the whole invasion in its tracks. Okay, so to pull that off, you've got to find the most important piece of that machine. And for a virus like SARS-CoV-2, that critical piece happens to be a very specific and thankfully a very vulnerable target. It's got a bit of a mouthful of a name, RNA-dependent RNA polymerase, or just RdRp for short. But its job is pretty simple. It's the engine that drives replication. Think of it like the virus's master copy machine. So if you can find a way to jam its gears, the virus is dead in the water. It just can't make more of itself. This makes RdRp the perfect lock for scientists to try and pick. Now imagine trying to pick this tiny molecular lock in a real lab. You've got thousands, maybe millions of potential drug keys. It would take forever. So what do scientists do? They've basically moved the whole lab into the computer, using some incredibly powerful simulation tools to work way faster and smarter. The first tool they've got is something called molecular docking, and it's pretty much what it sounds like. It's a hyper-realistic simulation where you take a 3D model of that viral protein, that's our lock, and then you digitally test how well all these different drug molecules, our keys, fit inside it. The snugger the fit, the better the chance the drug will actually work. But here's where it gets really, really cool. What if a key isn't just about its shape? This is where the next tool, molecular quantum similarity, comes in. Instead of just matching physical shapes, it looks at a molecule's electron cloud, its unique electronic signature. It's a quantum-level approach that can see hidden connections that just looking at the shape would completely miss. All right, so what actually happens when you unleash these digital tools on a bunch of potential antiviral drugs? Let's take a look at what the research found when they tested them against the virus's copy machine. So first up, let's look at remdesivir. You've probably heard of it, and yep, the simulation shows it's a fantastic fit. Look at that, it just slots right into that keyhole, the active site of the enzyme. And even more importantly, it makes multiple really strong connections. It's like a key that doesn't just fit, but clicks firmly into place, totally jamming the works. And the simulation doesn't just stop with known drugs. They threw in all sorts of stuff, even something as common as vitamin C. And what do you know? It also finds a way to snuggle into that same active site, making its own strong connections with the lock. This just goes to show you the power of this digital approach. You can test thousands of different keys super quickly to see what might fit. And listen, this was just the tip of the iceberg. The researchers tested a whole library of different compounds. The idea wasn't just to find one perfect key, but to build this massive database, like a virtual encyclopedia of how all these different molecules interact with this one single critical viral lock. But honestly, the biggest aha moment of the whole study, it didn't come from just checking if the key fit. It came from that quantum analysis. And it revealed something that kind of flips our whole understanding of this on its head. Okay, so we all get the lock and key thing, right? You'd think two keys that fit the same lock have to look pretty similar. Well, at the quantum level, not so much. It turns out you can have molecules that look totally different. I mean, nothing alike structurally, but they can have an almost identical electronic signature. And this table right here, this is the proof. It's wild. Look at this pair, emtrixabine and abacavir. If you look at their physical shape, they're only about 60% similar, but electronically, they're at 0.93. That's almost identical. It's like they're electronic twins. This is a huge deal because it means the virus isn't just looking at the shape of the key, it's feeling its electronic charge. This insight changes the whole game. So what does all this mean for the future, for the next pandemic? Well, the biggest takeaway here is that this research helps us write a brand new and much, much faster playbook for finding cures. This basically gives us a new blueprint. First, you find the virus's weak spot, the lock. Then you use molecular docking to test millions of keys virtually. Step 3, you bring in the quantum analysis to find those electronic twins even if they look different. And then, and only then, do you take the absolute best of the best into a real lab. You can see how this saves an insane amount of time and money, right? And why does that matter? It's all about speed. By doing the heavy lifting in a digital world first, scientists can create these incredibly accurate blueprints for new drugs. They can figure out what won't work without ever wasting precious time and resources in a lab. We're talking about cutting down drug discovery from years to maybe just months. And that leaves us with this one last pretty amazing thought. We know what kinds of viruses are out there. We have a good idea of what their master keyholes generally look like. So with these incredible tools, these quantum simulations, could we actually start designing master keys in advance? Have a whole library of them ready to go the second a new threat appears? It sounds like science fiction, but we are getting closer to that reality than ever before.